Good afternoon, dear students. Yesterday we had the lesson about linear operators, and today we are continuing studying a theory of linear operators, and our topic is eigenvectors and eigenvalues. Uh, Maybe anybody remembers what such terms mean, definitions. Dmitro?
If I'm not mistaken, an eigenvector is a vector that we multiply by a matrix, but it keeps its direction.
Yes, so eigenvector, yeah, basically it's such a vector, and uh, if we are multiply it by so if we apply the linear operator to it, it is so if we apply the linear operator, it always multiplied by lambda, which is lambda coefficient, which is eigenvalue. Vadim?
I have a small question. It's not about our lessons, some more about the linear. We have like ninth lecture or practical lesson attendance for yesterday for 22nd.
Mm-hmm.
Yeah.
Okay, just a moment. I will correct it for you. Yeah, my bad. Okay, we'll change it. So now it must be available. Try to mark your attendance. So verify if it works, and we will move next.
I'm sorry, I still have marks that I was missed on this lesson.
Okay, let me check. So, by the way, who was asking?
Carbon.
Mhm. Is it available for you now to mark your attendance? Because as I see, some of you are present, some of you not. So
No, I have a mark that was missed. Yeah, Nebu.
okay,
Still, and I can't press. Yeah, anything.
yeah, I will just change it. But so if anybody else has problems with attendance, please write me. So everyone almost. Yeah. Okay. Just a second. I will recreate the lesson, and I guess we will have no problems. So I will delete this one and create a new. Try now.
Everything is correct.
Okay.
In
So
mind.
okay. And what about others? No, as I see, no problems.
Works.
Almost. Mm-hmm. Good. Okay. So now moving to our topic, to our lesson. So this is actually the kind of definition of eigenvalues and eigenvectors. Yeah, these terms came to us from German, so such interesting pronunciation. So eigenvectors are such vectors which when we apply the linear operator to it as the result, it will be a vector multiplied by lambda, so which is an eigenvalue, just a scalar number. Generally speaking, eigenvalues and eigenvectors are so they are not used only for linear operators, just generally for matrices. And now we're talking about linear operators given by matrices. So who remembers how to find eigenvalues and eigenvectors? Who wants to answer? Bogdan?
If I remember it correct, for eigenvalues, we can use the formula that says the matrix A minus lambda times identity matrix. And we need to find the determinant of this and make it equals to 0 and then solve the equation.
Yes, correct. But I will better move this formula higher. So, yeah. And we'll separate our formulas from tasks. Okay. Yeah, that's correct. So we calculate such determinant and find characteristic. This is a characteristic equation, and roots of characteristic equations are eigenvalues. So let's do it. Oh, nobody told me that I missed lambda here. Okay. So calculating like a usual determinant. Now this is 0. Okay, 0, nice. So minus 1 minus lambda. I use here square brackets just for convenience. So they're equivalent to round brackets. Just for easier, just for convenience, and that's all. Okay, so this element, then it is 0, and this is 0. And double check the main diagonal. 0, 0. Okay, so we even don't need such brackets. Okay, good. And now let's expand, or even, we don't have even to expand it, by the way. So we can just move this 1 minus lambda out of brackets. So basically it gave us nothing, so let's expand, and now and then we will see what will happen. Now So what can be simplified? And we don't need these brackets as well, but okay. We will remove them later. So minus lambda square plus 5 minus 5 minus lambda cube plus 5 lambda square, then minus 8 plus 1 minus 7 lambda and minus 3. So let me check if nothing is missing.
Then it'd be like plus 3.
Minus, yeah, thanks. So, of course, yeah, so losing a sign, it's not a good practice, but thanks for your attention. Okay, now let's try to guess some of these values. Okay, so oh yeah, we could simplify it, by the way. So it could be simplified. So okay, that's was redundant. Such things. So let's now return back to this. So I will move 1 minus lambda out of brackets. Then 2 minus lambda square minus 1. And we know that 1 is a root, but we need to find 2 more. And this, of course, will be expanded. So 1 minus lambda. Then 4. By the way, let's write it short of 3 minus 4 lambda plus lambda square. And we just need to find the root of this equation. So 1 minus lambda. So let's use the Viet theorem. So it seems that roots are 1 and 3. So lambda minus 1, lambda minus 3. Yeah, so it seems to be correct. So lambda 1 and 2, basically. So we have two same roots, so we can rewrite it. So 3 minus lambda. So let's move a minus here, and we will have lambda minus 1 square. And lambda 3 is equals 3. Okay. And who remembers how to find eigenvectors? We have already found eigenvalues, and the next point is eigenvectors. Who remembers? Oh, nobody. Sophia?
We need to multiply it by the matrix with unknowns, like x's. Our
So
matrix or no.
So do you mean I guess yeah, I see you partially you are right. So you mean that we need to solve a system of linear equations, right?
Yes, yes.
Yeah, but it will look like the next. So A minus lambda E x equals 0. Yeah, so homogeneous system. Yeah, but you were right. And we need such metrics. Okay, so for lambda 1 and 2. By the way, what do you remember about such term as multiplicity? Who remembers? What does it mean? So we have two same lambdas, two same roots. So multiplicity of
Multiplicity equals 2.
yeah, multiplicity of this lambda equals 2. Let's mark it as k. Yeah, and it means that we'll have two general solutions. Yeah, well, we'll have one general solution, but we will have two eigenvectors that correspond this eigenvalue. And they can be found as a fundamental solution system. Basically, two any linear independent solutions, but fundamental system is the most convenient way. Okay, let's start. So A minus lambda E. Okay, we'll just copy and paste it. And we'll modify these values. So 2 minus, okay, I will write here that equals 1 just for our convenience. So here will be 1, 0, and 1. And what we will have, so 1, 0, minus 1, because so we see that 3 equivalent rows. So it can be, this row can be changed in such way. So what we have here. So x1 is a basis variable, and x2, x3 are free variables. So let's write. So we have only one equation, and x1 equals x3. X2 can be any number, so it doesn't even depend on x2. So Yeah, x3 is equals c oh yeah c2 and x2 will be equal c1. Okay, and they are real numbers. So c1, c2, and x1 will be equal c2 as well. And let's find a fundamental solution system. So x1, 0, so it equals, oh, my bad, c2, 0, 1, 0. And the second fundamental solution and these are eigenvectors for lambda 1 and 2. And let's find for lambda 3 as well, that is equals 3. Its multiplicity is 1. So here we have -1, -2, and -1. So this row will be eliminated. Then let's swap this, change the sign first of all, and this row will now be without changes for now. Here just zeros. And now let's just subtract the first row from the second. Yes, Sophia, you do have a question?
No, you changed the sign of the first row. It should be plus.
Yeah.
one. Yeah.
Yeah, thanks for your
That's it.
attention. So it will be plus, but let's just erase it. Okay, so 0, -2, nothing changes, and -2. And finally, when we simplify everything, here we leave just 1, 1. Okay, and now let's write the shortened system. So x1 plus x3. I left space on purpose. Just for convenience. So what we have? Okay, so vector. So the solution will be the next. Something is so I'm missing something. Yeah, but here we need only one solution because there's no multiplicity one. So we can one basis variable here, and oh, by the way, yeah, here we have just so my bad, two basis variable and one free variable because of rank 1. So it was a little bit incorrect. But no. Okay, yeah, it seems to be correct. Yeah, so the general solution will be the next. First of all, let's better express x1 as x minus x3 and x2 equals minus x3. By the way, they are the same. Okay, and here we can also select any variables. Well, something is yeah, a little bit confusing. Just a moment. Let me check where I made the mistake. So let's return to this one. So here we need two eigenvectors. So but yeah, so two vectors. Just a moment. So this is correct. Yeah, so this solution. Yeah. Minuses. And now everything is okay. So yeah, it was my bad. So and what we have here. So let's set, for example, C1 and C2. Oh, by the way, it must be, yeah, it must be only one. Only one linear independent. Yeah, by the way, we need, yeah, a little bit confused. So why such misunderstanding though. The rank of this matrix is 1, but we need the rank, so not not the rank of the matrix, but n minus rank a minus lambda e. And in this case, it equals 2. That's why 2 eigenvectors, 2 solutions. And in this case, a n minus this rank of this matrix. So rank of this matrix is 2. So it equals 1. That means that we have only one a linear independent solution, so we just have C. And now let's write the fundamental solution system of solutions. So it will be -1, 0. And this is the answer. So we found all eigenvalues and eigenvectors. Any questions about this task? Okay, it seems that no questions. Yeah, I will try to make solutions here for you as well, if I have time. But I guess that the weekend will have. Task number 2 is to find eigenvalues and eigenvectors of linear operator in a complex space. So or y in complex, yeah, we see that the matrix has real coefficients, but who get, maybe anybody guesses why complex space? Okay, because of the eigenvalues will be complex. That's a spoiler. So doing the same what we were doing before. So we need to find roots of characteristic characteristic equation. So let's start. Hmm. Okay. Lind. So this will be 0. 20 by 9 plus 180 minus minus 28 minus 4 minus lambda 0 and minus 5 minus lambda. And now let's expand. So, okay, nothing can be simplified like in previous task, but okay, here we will have to expand the brackets. Okay, for minus lambda, let's write it as okay, so no, for plus lambda, but we will move minus here, so it will be 5 a lambda plus 5 plus 108. Okay, minus plus 28. By the way, 3 minuses, so just minus 28 for plus lambda, and minus okay, plus 5 minus lambda, and now expanding everything, so 16 minus lambda square. Okay, we remain it without changes, lambda plus 5, and then plus 180 minus 28 by 4 minus 112 minus 28 lambda plus 25, not a good plus. Plus 25 minus 5 lambda. Okay. So what happens here? 16 lambda plus 80 minus lambda cube minus 5 lambda square. Okay, and what we have here? Plus, so 180, so 205 minus 112, and it will be 93. Yeah, so 180. Yeah, 93 minus 33 lambda. Continuing simplifying everything, lambda 3 minus 5 lambda square. So 16 minus 17 lambda plus 173. Okay, not so good. Not so good roots seem to be so not a good so good numbers, but or maybe yeah, maybe I'm missing something. Just a moment. So 16. It should be simplified in a better way. So maybe something with the signs. Just a moment. Sophia, yeah.
I guess here should be minus, no?
I moved minus. Minus. I was lost it here. So what I was. Yeah. So I decided to move minus into these brackets. So it must be a lambda minus 5. Yeah. Thanks for your attention. Okay, and here lambda minus 5. And now minus 80. So minus this, and plus 5 lambda square. Or not. Yeah, something is wrong here. Just a moment. Yeah, so minus here, here plus, minus, and here will be a plus 13. Yeah, and now everything is okay. Okay, let's rewrite it. So in the next way, so for the senior coefficient, we'll put plus. Minus 13 equals 0. So now lambda, okay, let's substitute, for example, with 1. So lambda 1, yeah. So if we substitute with 1, so 1 plus 17, 18, and here minus 5, minus 13, so it is correct. So lambda 1 is 1. And as I guess, we have a pair of complex conjugate roots for this equation. Okay, and let's find them. Not such interesting procedure, but there is no way to solve in another way. So we will divide this polynomial by lambda minus 1. So lambda cube minus lambda square, and it will be so minus 4 lambda 2. Minus 4 lambda 2 plus 17 lambda minus 13. Okay. Stop. So the first lambda is 1. But yeah. Yeah, okay, moving next. Okay, so minus 4 lambda. Minus 4 lambda square plus 4 lambda. So what remains here? So 13 lambda. 10 lambda minus 13. Something is wrong. Okay. Just a moment. I will solve it online. Yeah, it's not the main goal here to solve cube equations, but to find eigenvalues and eigenvectors. Okay, and what we have the next, so lambda 2 and lambda 3, yeah, they are complex conjugate numbers. So and they look like this. Okay, And now let's find let's clean it first of all. Let's find eigenvector for lambda 1. So here is our matrix. And let's eliminate everything that we can eliminate. So minus 3, 5 plus 15, 10. So 7 minus 27 minus 20. And here, so 0 minus 20 minus plus 36. So 40. So we can simplify it. Okay, and let's move next. Okay, and then 1 minus 2.
Sorry, we don't see your
Oh,
presentation.
sorry.
У вас презентація вимкнулася.
Yeah. So nothing. So now continuing. Okay. And what we have. So
Sorry, I have a question.
yeah.
I don't really get what we are doing right now.
On which point?
So we substituted the lambda to the matrix, right?
So yeah, we solve the next system A minus lambda E, and in current case, so we solve the next equation system. So yeah, and here we substitute lambda with the 1, so it looks like this: A minus E x equals 0. So
Oh yeah, I see
have
it.
I answered your question? Yeah.
Yeah, thank you.
Okay, let's continue. Okay, so as as we have only so multiplicity is 1, it means that we have only one eigen vector. Yeah, so one eigenvector that corresponds to this eigenvalue. So let's set so let's write in this way. But it seems that maybe something is incorrect. Sophia? Yeah.
I don't know what is incorrect, but I have a question. How
Yeah.
do you know that we will have only one eigenvalue?
Uh,
With this formula n minus rank?
n minus rank. Okay, so uh, how? So we have this eigenvalue, which multiplicity equals 1. It means that only one eigenvalue corresponds this. Only one eigenvector corresponds this eigenvalue.
Okay, understand. Thank you.
Yeah, and also now let's eliminate 0. Let's eliminate 5 here. So I just for our convenience. So if I add this equation multiplied by 5, so x minus, so x minus x1 minus x3. So how it will look like. And it will equal 0. So what we have, x1 equals x3 and x2 equals 2x3. And x3 equals c. And let's write fundamental solution system that will be equal. So 1, 2, and 1. And this is the eigenvector for lambda equals 1.
Sorry, I have a question.
Yeah.
Why did we remove -5? So like -5x2, or in the matrix there's 1, -5, and 9. So x1 minus 5x2, 9 plus 9 x3, right?
Yeah, but I did it. So why I did it? In order to eliminate x2 from this equation, and to have the ability to express x1 with the x3. Have I answered your question? So
Sorry, could you repeat that?
I eliminated x2 in order to express x1 using x3. So
Oh,
just
so we multiplied with 5
multiplied
and
by
oh yeah,
5
yeah,
and
I see it.
added
I see
to
it.
this equation. Yeah, so that's what we were doing a lot of times. Okay, and now what we have already. So we need to find the same for this complex value. But maybe we will start it, but I'm not sure that we will have a lot of time for this. So how the matrix will look like. Mhm. It has such multiplicity. Okay, it will be better to leave more space. So minus 2 minus 3i minus 6 minus 3i, and 3 minus 3i. Okay. So that's not such convenient system, of course, to solve.
Sorry, I have a question again.
Yeah.
Where did this complex number come from?
It is the root of characteristic equation. I just solved it online to save our time.
Oh, okay.
Okay. Yeah. So Gaussian method is not such so convenient here. So yeah. Any questions?
No, it's not a question. Can you save this paint file and maybe add to the DNR so we can check it?
I will do the next. I will write a detailed explanation for each task. So
Oh, it will be
even
good.
better than paint file.
Okay.
Yeah.
Okay.
Yeah, because it needs more explanation for each task. Okay. And what do we need? So Gaussian method is not convenient here. But we can simplify our calculations. So for example, so we can take a basis minor. So basically we can choose any minor of this matrix, and let's choose, for example, this one. This basis minor. So we will reduce our system already to two equations. Okay. So how are we going to do it? So we will just eliminate this row and take to this. Yeah. First of all, we will define the rank of the matrix. Of course, we have to change. We'll have to check the minor if it's equal to 0 or not. And basically it's not equal to 0. So minus 4. Yeah, 6 plus 3i, and we can move also 3 out of brackets. Okay. So it means that we have only one eigenvector, so rank of this matrix equals 2. So n minus 2. Okay. And then let's find our so let's first of all write the reduced form, or reduced matrix for 6 system. and let's express our variables. So what does it equal? So x1 equals 3 minus 3i. Yeah, and x3 of course not to lose it. So minus 3 minus 3i multiplied by 4. Okay, and so that's it. And let's and don't lose the variable. Then x2. Okay, it will be equal. Okay, we need to express everything. Okay, let's write it in such a way. So 6 plus 3i. So we need to divide it by this coefficient, and then minus 9x3 minus x1. I don't like dividing by complex numbers, but what to do? Okay, and now, so x3 will be the free variable. So in order to simplify our calculations, let's first of all mark it. So let's give its value. So 4, and we'll easily get this value. So x1 will be equal 3 minus 3i. And then x2 so minus 36 minus 3 plus 3i. And just a moment, I will calculate complex numbers, because just to save our time. Just a moment. And it will be equal 5 minus 3i. So eigenvector for this eigenvalue is 4, 3 minus 3i, and 5 minus 3i. Okay, analogically to complex conjugate value, and now we will have a break, and then move into other tasks, because we spent a lot of time on this one. Any questions maybe for now?
No question.
Okay, so let's have a break, 5 minutes, and then we will continue. Okay, let's continue. So now moving to the next task, we have to transform matrix A of a linear operator to the diagonal form.
I have a small question.
Yeah.
Yeah. I think this example was a pretty big. Yeah, I'm sure about it. Yeah.
Yeah.
Will we have such questions on maybe on exam or maybe tests?
On exam, they definitely will be smaller. So usually on exam, like two by two or something like that. Of course, I'm not sure 100% because I won't give your exam, so you will uh, pass it to Svetlana Mykolaievna. So the lecturer always. Gives exam. But
Okay.
usually, just to save time, the dimensions are less. Okay, so now let's do this. So let's transform to diagonal view. If you have no questions, but if anybody has questions, first of all, I will answer. Okay, no questions. So, question from me, how to solve this task? Okay, no questions. You don't remember. Well, first of all, of course, we need to find eigenvalues and eigenvectors. And then we will so with using eigenvalues and so with using eigenvectors, we will move to the bases formed built on them, and well, then we will have the same that we were doing yesterday. So move to another basis with the transition matrix, and for this we will have to find eigenvectors, eigenvalues. So let's start solving. And by the way, we see that this matrix is symmetric. So it means that A means A transposed. And it means that all lambdas are real numbers. That also simplifies the task. So lambda 2 minus 5 lambda equals 0. Okay, let's simplify it. So lambda 1 minus lambda minus 5. So let's move lambda out of brackets. It equals 0. So it means that lambda 1 equals 0. Lambda 2 equals 5. Okay. Sorry. Now let's find eigenvectors for this matrix. So for the case lambda equals 0, so we just solve this matrix. So matrix A doesn't change, and what we basically have that 1, 2 row doesn't remain, doesn't change, and this just can be eliminated. And what we have, x1 equals -2 x2. So x2 is a free variable, and what we have, e1. By the way, we have only one solution here, a general solution, fundamental. So if we set x2 equal to 1, and so x1 will be equal -2. Then for lambda 2 equal to 5, okay. Then next. -4 -1. And we have the same situation, so 2 -1 0 0. And x1 x2 equals 2x1. Okay, let's set x2 as 1 and x1 equals no, let's do the next. So yeah, let's set x2 as 2 and x1 will be equal 1. So eigenvector for this eigenvalue is 1 2. And now let's move to the, let's transform matrix A to diagonal form. So how to do it? We build a transition matrix, what we were doing before, based on eigenvectors. Okay. And we inverse it, of course. So T1 2 is 2. Oh, T1 1 is 2. T1 2 is -1. T2 1 equals -1, and T2 2 equals -2. The determinant of T, so -4, -1, -5. So the inverted matrix equals -1 by 5 multiplied by 2 -1 -1 and -2. Okay. And then we need to find the diagonal matrix. So let's mark it as D, and the formula of transition to other bases. that we already know. One, two, two, four. Uh, 2 minus 2, 0. Then, yeah, 2 and minus 2. 4 minus 4, 0. Minus 1 minus 4. Yeah, minus 1 minus 4 is minus 5. And then minus 2 minus 8 minus 10. And multiply by this matrix. So 0, 0, 10, minus 10, 0. Yeah, and of course, don't forget to multiply by to divide by determinant. And here minus 5, minus 20, so minus 25. And it will be, so the next from it will have, so 0, 0. So this is the diagonal matrix. And who knows, who can answer what we have in this diagonal matrix? So so what do these numbers mean on the main diagonal? I will move upper. So did anyone notice, or maybe you just know theory, remember it? No? Okay, so let's look at these eigenvalues and then look at main diagonal. So what can you notice?
That this has elements of the main diagonal.
Yeah, so it equals yeah, so also yeah, it equals eigenvalues. So and we also can write it like that, diagonal lambda 1, lambda 2. So when you transform a matrix to diagonal form, so verify that lambdas are on the main diagonal. It will mean that you were right, that it's correct diagonal matrix. Of course, answers where you just write eigenvalues on the main diagonal, they will not be accepted in your individual tasks, of course. You will have to prove it to verify that you found all values correctly. Okay. Maybe you have any questions about this task? It seems that no questions. Okay, let's So one more task, and then we will finish. Okay, about task 4, I have a question. Uh, so can you answer? So can you answer if how to determine how to define if the matrix can be transformed to diagonal form or not? Okay. Uh, so now we won't stop on task 4 because we already know how to transform to diagonal form, and I will provide you the solution. And what so how to define if we can how to determine if we can transform to diagonal form. So the following: if we have if we actually can find all eigenvectors. So in some cases we cannot find eigenvectors uh, correspondent to each eigenvalue. So for example, we have eigenvalue with the multiplicity 2, but the rank of the matrix is uh, is 2, so it means that we can find only one eigenvector. So if we can't find all eigenvectors, so if not a full set of eigenvectors, it means that you won't be able to diagonalize the matrix, because you won't be able to build a transition matrix. Okay, maybe any questions about it for now? No questions. Okay, now we'll move into task 5. And so we will doing almost the same thing that we were doing in the previous task, but maybe. So do you remember what does orthogonal matrix mean? No? Okay, I will explain you while we're doing the task. And now let's first of all find eigenvalues and eigenvectors. 9 minus 6 lambda plus lambda square minus 1. So it equals lambda square minus 6 lambda plus 8. And so what we have, and with theorem, yeah, so 4 and 2. So lambda 1 is lambda 1 equals 4. Lambda 2 equals 2. Okay, and now let's find eigenvectors. So the eigenvector for lambda 1 minus 1, minus 1. So x1 equals x2. And let set, so we'll set the value of 1. So 1, 1. And now we need to orthogonalize this vector. So we need to normalize it. How to do it? Does anybody remember how to do it?
No.
We have to divide the vector by its magnitude. And that's it. So the magnitude of the vector, so we need to normalize it. The magnitude of the vector is the square of 2, and what we have. So we need to do it for orthogonal matrix. It has a very useful property, maybe you remember it. Important property of orthogonal matrix. No? Okay. We will move to it soon. So in this case, x1 equals minus x2 equals c. So the fundamental system is 1 minus 1. Oh, no, vice versa. Minus 1, 1. And we need to normalize it as well. So minus 1 by square root of 2 and 1 by square root of 2. And now we will build the transition matrix, which is orthogonal. Yeah, I know the time is up, but let's finish it, and then you will be free. So the most important and the most useful property of orthogonal matrix that inverse of matrix will be equal to the transposed matrix. So we won't have to find a determinant of this matrix cofactors. We will just transpose it, and that's it. And the determinant of orthogonal matrix equals 1. Okay, so let's diagonalize quickly, and we will be free. Okay, here I will just accurately change signs. So transposed this matrix. Then our initial matrix 3, 1, 1, 3. Okay, let's count quickly. Let's calculate quickly. So 3 plus 1, so 2 by square root of 2. Then 1 plus 3. Oh, no. So here 4 square roots of 2. Yeah, because 3 plus 1, 4 square roots of 2, and 4 square roots by 2 as well. And here, so minus 2 by square root of 2, and 2 by square root of 2. Multiplying by this matrix. Okay, so now 4 by 2 plus 4 by 2 equals, so 8 by 2 equals 4. Then 4 by 1 minus 4 by 1 plus 4 by 1. So of course, so 0 minus 2, 2, 0. And here, so 2 plus 2 plus 2 and divided by 2. So 4 by 2 equals 2. And here is the diagonal matrix that contains the lambda's eigenvalues on the main diagonal. Any questions about this task?
No question.
Maybe about the lesson in general, about previous tasks. Okay, so have a nice day. Stay safe. Thank you for your attention. And I will provide you explanations for each exercise soon.
Thank you for the lesson. Goodbye.
Thank
Have a
you,
nice day.
goodbye.
Bye.
Goodbye.
Thank you. Goodbye.